In this video, we're going to go over a step-by-step method for drawing all the isomers of a compound, focusing especially on the constitutional or structural isomers. So let's have a quick review of the types of constitutional isomers. We have the skeletal isomers, which are different carbon skeletons. It can be a straight chain, or we can have shorter chains with some branching. Then we've got the regioisomers, which have the same carbon skeleton, but the functional group is in a different position. Then we have the functional group isomers, which have different functional groups. So when it comes to a problem like this, you probably don't want to just start guessing and trying to draw some compounds. You want to have a strategy and a method for approaching this sort of problem, so that's what we're going to go through here. So step number 1 is going to be to find or calculate the degree of unsaturation, which is equal to the sum of the number of pi bonds and rings in the compound. So if you're provided with a structure, you can just count pi bonds and rings. Remember that a double bond has 1 pi bond and a triple bond has 2 pi bonds. But if you're given a formula like we are here, then you're going to calculate the degree of unsaturation as follows. 1/2, 2 times the number of carbons, plus 2, minus number of hydrogens, minus number of halogens, so fluorine, chlorine, bromine, iodine, plus number of nitrogens. And oxygen is not in this formula because it doesn't affect the degree of unsaturation. So we're going to go ahead and calculate the degree of unsaturation for this compound here. So we've got 1/2, 2 times number of carbons, which is 3, so 2 times 3 is 6, plus 2, minus number of H, which is 6, 1/2 of 2, which is 1. So this compound can have either 1 pi bond or 1 ring. So step number 2 is to list out the different possible combinations for the functional groups. So if the compound has 1 pi bond, it has to be a double bond because a triple bond would require degree of unsaturation of 2. So then we look at the formula. A double bond could be a carbon-carbon double bond, or it could be a carbon-oxygen double bond. So in the case of a carbon-carbon double bond, the oxygen would have to be singly bonded, so it would have to be an alcohol or an ether. And in the case of a C double bond O, it would have to be part of either an aldehyde or a ketone. And that's your pi bonds, and then we could also have 1 ring, and of course no pi bonds. So that would mean that your oxygen again would have to be an alcohol or an ether. So step number 3 is going to be to draw the compounds. So my formula is C3H6O. And I'm going to start with the C double bond C with alcohol. So I have a 3-carbon chain, and I'll put my double bond, and then my alcohol can go in any one of 3 positions. So we'll draw those out. And no branching is possible here with just 3 carbons, so that's it. And then we'll move on to the C double bond C with ether. So ether needs to have carbons on either side. That's 2 carbons that I've used, and now I have 1 more, so I'll put it here. And then I need a double bond, and the only place that can go is here. So that's the only possibility for the ether. Then I'll move on to the C double bond O. 3 carbons. For the ketone, it would have to be here in the middle. And then the aldehyde have to be on the end. And those are the only possibilities there. Then I can move on to the ring with the alcohol. The biggest ring possible is 3 carbons. And then the OH will go anywhere on the ring. That's the only possibility there. And then I can move on to the ring with ether. So if I try again the smallest ring possible with ether, the ether would need another carbon on the end, and that's 4 carbons, so that's too many. Which means that your ether has to be part of the ring. So we're going to make the biggest ring possible, oxygen, 3 carbon, so 4-membered ring. Then we're going to make a smaller ring with some branching. So 3-membered ring with methyl group. So these are all of your structural isomers. Just note that 2 of them are enols. So they are alcohols on a alkene, which are not stable, and they tautomerize to these structures. So those are your isomers for C3H6O. Let's move on to one more example, C5H10. So we'll do step number 1 again. Degree of unsaturation, 1/2, 2 times carbon, 2 times 5 is 10, plus 2 minus number of H, which is 10. So again, we're going to get degree of unsaturation of 1. And it could be 1 pi bond, which would have to be C double bond C, or it could be 1 ring. So basically this would be a cycloalkane. So we're going to draw a series of alkenes and a series of cycloalkanes. So for the alkenes, we're going to start with the biggest chain possible, which is 5 carbons. And then we'll put the double bond first here at carbon number 1, and then here at carbon number 2. And if we try doing it over here, it's the same as the previous molecule, so that's all that we can do for the 5 carbon chain. Then we'll do a shorter chain, 4 carbons with 1 branch. And the branch obviously cannot go on the end, so we're going to put it in the middle. And then we put the double bond, starting on the left, going to the middle, and here on the right. Then let's try maybe a 3 carbon chain with 2 methyl branches, but that doesn't work because there's no place for the double bond. That's 5 bonds too many. So you could also try maybe an ethyl branch, but that's the same skeleton as the previous row. So that doesn't work. So that's it for the alkenes then. Let's move to the rings. We're going to start with the biggest ring possible, 5 carbons. Then we make a smaller ring with some branching, so 1 branch methyl. Then a 3-membered ring, and you can have 2 methyl groups as a branch, or you can have the methyl groups like so, or you can also have an ethyl branch. And those are all of the rings that we can make. So these are your constitutional isomers. Now, if you want to draw all the isomers, you have to include the stereoisomers, and those would be cis-trans alkenes, of which here there's only one possibility, which is this one. You can make the cis version of it. And you also want to look for chiral carbons, and here there's just one structure with chiral carbons, which is this one. So you can make maybe a ring with cis methyl groups, 2 wedges or 2 dashes. And then you can make the trans version. So a dash here, a wedge here. Or the enantiomer of that molecule, which would be wedge here and dash here. So those are all the isomers of C5H10. So I hope this video was helpful for you, and I hope to see you again soon.